So we are going to go ahead and talk about event-related potential designs and then how we can use those to address the locus of selection problem. So what are event-related potentials? These are a way for us to measure voltage differences across different electrophysiological responses as a result of a direct applied stimulus. So a couple ways we can do this. We can do this using EEG or single unit recordings. So if you take a look to the right of the screen, you'll be able to see some examples of what those look like. So basically, taking those two methods, we can collect data across multiple trials. So we want to do this as many times as possible. And then we want to try and average it and create some kind of, line plot of this data. So we average it, we time lock the stimulus, meaning that we apply the stimulus about the same exact time every time during the trials. And then the stimulus is also going to be identical. So we don't want to have any differences across trials. So both of these methods give us a really high temporal resolutions that allow us to look at things within milliseconds. So what's really nice about this is it allows us to give kind of a cause and effect observation because we are able to apply stimulus and then directly observe a physiological response as consequence of that stimulus. So it's really good for trying to establish these cause-effect correlations. So what is the locus of selection problem? Well, it looks at our visual attention tasks within the brain. And we know we have two streams. We have a ventral and dorsal, but here we want to focus on the ventral or the what stream. So we have two competing theories in relation to this ventral stream about where we start to have filtering occur in this information processing stream. So if you look at the left, here is our ventral stream. And this is what we would use to kind of conceptually describe how it works. So two competing theories are early and late. So the early selection occurs earlier on down the stream, later selection occurs later. So at that point, we're trying to decide where we start to filter out this information. So at what point does selection happen in this stream? So how can we use ERP for this? Well, we can map our ERP responses against those stages that we just delineated previously. And then we'll use two different testing blocks, one of an attended Q trial and one of an unattended Q trial. So we can then compare the results of those two testing blocks using the same timescales, and we can try to map those voltage differences to the different cognitive events and associated areas. So here on the right side, you can see EEG, figure B, and C and D are the single unit recordings. So again, remember, we are time locking our stimulus. We're looking for event related signals. So the stimulus applied, what do we observe? And then we're doing this over multiple trials. Okay, so this is how we get the data in the bottom right. So our interpretation from the ERPs, well, we would, in relation to each other, V1, V2, and V4, the three main areas we're looking at here, they aren't too far away from each other. However, V1 is more upstream and V2, V4 more downstream. We actually see no effect in V1, and in V2, V4, we see a difference in amplitude, a considerable difference where we can effectively say it has been affected between the two testing blocks. So even though one's upstream and one's downstream, in relation to the grand scheme of things here, we actually are in more support of the early selection theory. So V4 is still considered an early visual area. The reason being is the inferotemporal cortex is considered the final stage. So you have the attentional cues, your sensory detecting them, and then you're going into object recognition is where the IT cortex occurs. So here we are supporting the early selection.